blockchain security team at Coinbase, specifically the protocol security team. Um, and I guess we've had a lot of blockchains since Bitcoin. So far, this data is something I pulled from CoinGecko, but it has 275 blockchains being tracked currently on CoinGecko. And of those, we have like 89 layer ones, and we have more incoming. We have Tempo, we have Monad, we have some that are probably still in stealth and all. And all these blockchains basically have like different ecosystem. They have like, isolated states, which is not kind of public to other blockchains, because the way blockchains are built, the states are being isolated by default. And this brings up like some issues generally. We have like fragmented liquidity. We have like bad UX, which is basically a feature of each blockchain being different. Wallets are not compatible across some blockchains, which is also a feature of how the blockchains are designed. And here we also have the issue of like the TVL. So here we can see Ethereum has about 62% TVL, Bitcoin and other things. But these are what's about 10 blockchains with the largest top 10 TVL. But at the end of the day, we have so many blockchains, and each of them are promising, something great, something superb. They are promising the future of Web3. But they all cannot work together. And what's the solution for that? The solution is bridges, basically. So today I'll be talking about bridges, and then a few details about like the EVM and SVM. So the EVM is the Ethereum virtual machine, the SVM is Solana virtual machine, and just a few bridge vulnerabilities, and also talk a bit about the base bridge, which is being built by Coinbase. So basically, what's a bridge? A bridge is a protocol that connects different blockchains together. I mentioned earlier that each blockchain is isolated, so it's more like an island. And this Venn diagram I have up here just shows how blockchains are intertwined. They're basically isolated. So bridges are how you can actually connect different blockchains together. And there are different bridge architectures. So here is like a, framework of how I can visualize bridges. So we have your source chain, your destination chain. We have a user on both ends, and we have like an off-chain component. So if a user wants to bridge using like a lock and mint bridge, the user initiates the transaction from the source chain, and if they're sending ETH, because we had like an ETH event, so here they lock their ETH on the source chain through the bridge contracts, which emits an event and makes the call to the off-chain component. The off-chain component, which is basically validators, they kind of like verify the transaction and lock the ETH, and then also make the call to the destination chain, which authorizes the mint of ETH or wrapped ETH on the destination chain, which sends to the next address. And this is basically how all lock and mint bridge work. And obviously, through the redeem flow, it's kind of the same thing, just in reverse. So you burn your wrapped ETH, which makes a call to the off-chain components, which makes a call to your source chain contract, and unlocks your ETH on your source chain. But this is just one of the architectures, and I know that there are multiple. Ethereum is like an open source, protocol, and basically everyone can build anything they want, and we have multiple bridge architectures also, and these are just few I picked. So we have like the lock and mint bridge, and burn and mint, and then lock and unlock. The main differences between these are what is native on where. So for lock and mint, you have your native assets on the source chain, and you just have like a wrapped assets on the destination chain. For the burn and mint bridge, you have like native assets on both chains. So if, for example, if you have USDC by Circle, USDC is native both on Ethereum and on Solana and on Base. But you wonder, okay, how do you say it's native? It's because it's being deployed by the same entity, so they have the same contract, not just like a wrapped version on each of the individual chains. And then the lock and unlock bridge, it's basically a bridge that functions due to like liquidity providers on both chains, where you like lock your liquidity in a pool on one chain, it unlocks liquidity on the other chain. And we have examples for all of them here as well. So yeah, a little bit of blockchain VMs, and I won't be going too technical, into like blockchain VMs. But basically, blockchain VMs or virtual machines are the execution environment for transactions which interact with smart contracts. So anytime you send a transaction and that has to interact with a smart contract, it's been executed by the blockchain VM. And basically, I just have like a simple example here of sending USDC. So I know a bunch of security folks are here and they're ready to jump on like how many opcodes we have in just a simple transfer transaction. But this is dominated down into like just a simple flow. So a user is sending Alice and Bob. Alice sending USDC to Bob. So Alice initiates the transaction, and the transaction basically has a bunch of things involved, which is like a read compute. You have the compute of the actual deduction and addition of balances, and then the write the opcode as well. So that's kind of like an S load, the computer, and the S store. But of course, in like the native ERC20 transaction flow, we have like multiple S loads, M loads, and add and subtract opcodes in between. And then the state is being updated here. So that's like a simple, what I say, flow or example of how transfers work on VMs. But a more detailed, will I say, information about VMs in this case is between the EVM and the SVM. And why I picked both is because the base bridge being built by Coinbase is a bridge between Base and the Solana, which is basically these two VMs together. So major differences between the EVM and the SVM is how transaction is processed. So the EVM is a stack machine. Transactions are processed sequentially, one after the other. While Solana, due to sea level, basically offers parallel processing of transactions if the same state is not being touched. So basically, it examines the states that have been touched at the beginning of the transaction, and if the same states are not being affected, it can process those transactions in parallel. And I guess we have like a new L1, which is also promising like parallel processing for EVM. And another thing here is the state model. So on EVM blockchains, we have like contracts. They hold both their code and storage in the same address. While for Solana, which was much to my dismay when I started reviewing Solana contracts, we have things that are completely different. So you have to assign a specific account for storage and handle those in a specific way that adds another security layer over those. And then we have the gas fee model. So Ethereum uses the single fee markets, while Solana has like local fee markets. But this offers like some trade-offs between both of them. The first thing is if multiple users are trying to interact with the same program, which touches like similar states, then obviously fees spike quicker on the SVM. And on the EVM, if somebody is hosting like a large mint, a large NFT mint, that could cause like a gas spike for the whole blockchain. And these are constantly things that are being improved, in one way or the other by new EIPs, new upgrades to each network, but that's how it works. And then for the smart contract languages, I know we have a lot of languages aside Solidity and Viper. Philogil was mentioning Sensei, a new compiler he was working on, and we have like core Solidity, but it's all currently being compiled down to EVM bytecode, which is what is being used by the EVM. And Solana compiles Rust to SDPF bytecode, which is kind of similar. So bytecodes are basically the list of the opcodes and like the transaction and how transactions are actually being processed in this case. So it contains all the instructions which are being used here. So here I'll be going into a few bridge vulnerabilities, which are kind of like things I just highlighted, which are things I highlighted in this case here. So one of it is kind of like the relayer list. So on the relayer side, relayers in this case are the off-chain components. So you have like your two blockchains functioning. You have your source chain and your destination chain. But in between that, the communication channel, if it's being compromised or, for example, it's down, So we had like a Cloudflare outage a few days ago. We had an AWS outage, I think earlier this month or last month. And if your bridge cannot function without that, and there's no like decentralized signing that can enable someone to like send, or rather complete the message on the other side of the bridge, you have your bridge basically down for some hours or some days, and if possible, like it causes like loss of funds or some other risks. Another thing here is reorg risk. So this is something specifically complex to handle, especially when handling like multiple chains. So time to finality is a big thing. Here, I highlighted this too, but we all know time to finality on Ethereum is like about like 12 seconds. Base is about 13 to 15 minutes. Solana is about 13 seconds. And we have like multiple other chains. ZK chains take a little bit of more time, depending on what or how they are validating and posting their batches. But time to finality is a big risk, and if you have like reorg happening in the blocks, then obviously you would have to wonder, okay, how do you handle reorg risks such that you don't finalize a transfer of like $1 million on your destination chain, and then you have the transaction reorged on the other chain such that it never existed. And this is not exactly, it's something that could just happen, even through, like, it's not a direct attack vector if reorg cannot be like triggered on the other chain, but it could happen like a byproduct of, some miscommunication or something wrong happening in between like each chains. And for example, this is more prominent in like single sequencer chains. I know at a point when I started using the blockchain a bit on Polygon, I had some issues with like reorg and stuff depositing to centralized exchanges then. And I guess that's what my first intro to, okay, how reorgs could actually affect like real life usage. And then again, another thing is like replay attacks. So the function of the off-chain component in this case of the validators is to like sign a message that's been verified. So on your source chain, you sent like 100 ETH, and then you are bridging that 100 ETH to another chain, in this case, let's say another L2 or another like L1. And after the message has been verified and signed by the validators, someone broadcasts the message to the destination chain, and you mint your 100 ETH. But if that mint is not being tracked, the signed message can just be replayed over and over again. And I guess, companies like Open Zeppelin and other standardizations, like standardized EIPs, kind of like help with this, tracking your chain ID, tracking nonces. But if you're implementing something custom or on a chain that does not have like all these tools, you have to like track what messages have been signed, have they been used on the destination chain. If using them failed, how do you accurately track them such that they can be reused, or the funds are completely stuck, or how do you refund? So you have to handle that as well. So yeah, I think I did a simple slide here of how like you send the same signed message over and over again, and that would continuously mint the same transaction in the same way. So yeah, another thing which has been kind of the bane of Web3 is off-chain stuff. So here is private key compromise. You have the social vector. You have like committing your private key to GitHub directly. You have multiple things. But basically anything that can compromise your private key is a big attack vector, and which is why key security is kind of a big thing. You have to handle, or you have to make sure your keys are not just, you don't have like a single signer for your bridge, for example. So if you have like some, like some multi-sig where multiple people have to approve in different locations, so you don't have like a physical vector to your decentralized bridge. So I guess like there have been some examples. The Ronin bridge was pretty bad, and then we've had other examples as well over the years. But yeah, that's for private keys issues. Now, some bridge vulnerabilities on the smart contract level. I won't be going too deep into this, but we have basic stuff like reentrancy. So different bridges have different functionalities. Some bridges also enable like message passing, where the bridge can make a call to like a contract on your behalf. But if that enables like a callback, then you obviously have like a reentrancy attack vector here. You have like upgradable tokens. So for tokens, we have like multiple tokens such that like even the ERC20 token standard is not being followed to the letter. And when you have like upgradable tokens, how do you handle the token balances of your bridges such that it doesn't just go to zero? Or like what exactly is your, backup plan? Or how do you remove the liability risk here for like upgradable tokens for your protocol? And then we also have like malicious message calls, whereby you could craft a message that transfers the entire balance of the bridge to another address. So some people handle this by whitelisting message calls or blacklisting some function selectors. So you do not allow like special function selectors to be called through your bridge. And then we have decimal inconsistencies. So I'll just give a brief intro on this before I go. We have the Base Solana bridge, which kind of like connects Base and Solana together, where it enable different things, token transfers, arbitrary message passing. So you could make a call to a contract directly from Solana to Base. So you could basically call a deposit transaction on a Base contract from Solana. And we have like different security, features, which kind of like enable security. We have like validation of messages. We have a contract which kind of acts like the implementer or your msg.sender in this case, which does the execution calls for messages being passed from Solana to Base. And that is going to be mapped to every Solana address as its seed. And then we can enable like multi-token deployment. Yeah. So on the Base to Solana side, we also have like validator verifying deposits. We have you have to wait for finalization of messages to prevent like the reorg attack vector, which isn't really a thing for Solana to Base since we have like a shorter time. And also we can have multiple Solana tokens for one Base token. This is because of the decimal inconsistency. So if we have Rust security researchers here, they know that on the Solana side, the way decimals is being handled and your max UNT value is kind of different. We have the max of UNT 64 in this case. So UNT 64 to UNT 256 is kind of like a big jump. So here we kind of like enable like multiple token deployments with different decimal values while ensuring that the tokens can always be redeemed on the other chain that it came from. So yeah, that's basically the talk. But generally, you would want to secure a bridge to like multiple audits. Most of us here know what security is, I would assume. But yeah, if you become a builder, don't just assume that your bridge is secure because you've audited other contracts and stuff. And then end-to-end tests. Funny enough, I've audited multiple protocols where they don't have a full test of the full flow from transaction from like a first flow to the last flow. Even if it has to spam through like multiple transactions, you have to test that to see if there's no leakages. And this also involves like fuzzing and all. I've spoke to many amazing teams that have like different fuzzers, different state mutation testing and all. And yeah, another thing is monitoring. So there have been a lot of talk about monitoring over the years, but monitoring is kind of a big thing. If you have any protocol, including a bridge, monitor your funds, monitor your transaction flow, monitor anything you can monitor. The faster you catch it, the quicker you can react. And yeah, thank you.